Okay, power functions. That's like y equals x raised to some power. That's why we call them power functions. X is raised to a power. That's distinguished from exponential functions, and it's rare that somebody actually knows the difference. And yeah, a lot of people have had pre-calculus. I'm not sure how they come out without knowing the difference, but we'll see. If x is in the exponent, it's exponential. If x is being raised to power, it's a power function. There's a big difference. Okay, well, anyhow, this is how we define a power function. And it's defined for any value of p. It's going to be defined for when x is greater than 0. For any real number p, x to the p is defined as long as x is bigger than 0. Now, why isn't it defined for p equals 0? Well, I mean, the function is defined for p equals 0. If p is greater than or equal to 0, it's also defined when x is 0. Okay, now, the function isn't, some functions aren't defined when x equals 0 because p could be a negative number. So if you have, for example, 1 over x squared, well, that's the example we give here, and we'll talk about that in a minute. And we'll see why sometimes power functions are not defined when x equals 0. And sometimes they're not defined when x is less than 0. Okay? So, now if p is a non-negative integer, okay, integer like, p is 0, 1, 2, 3, 4, 5, 6, non-negative integers, then your power function is defined for all real values of x. The point here is that you have different conditions on the domain of your power function. And then, of course, you have the range of the power function that we're not talking about yet today. Well, let's do a few examples so we can understand why some of these statements are made. Okay, suppose y equals x to the negative 2. Well, that means p is your negative 2. It's your p equals negative 2 power function. X to the negative 2 is 1 over x squared. So this function is y equals 1 over x squared, just another way of writing x to the negative 2. And we know that if x is 0, this isn't defined, is it? So this is why I say we're always defined if x is greater than 0, but not always if x is equal to 0. If p is a negative number, it's not defined when x equals 0. Okay, y equals square root of x. Okay, well, square root of x is x to the 1/2, right? So that's the p equals 1/2 power function. First of all, p is not an integer. And we can also say that this function is undefined when x is less than 0, because if x is less than 0, it's negative, and we can't take the square root of a negative number, at least not over real numbers. Okay? So we see that this function is undefined when x is less than 0. We're familiar with this function. We understand that. And here's an example of a non-integer value of p that isn't defined when x is less than 0. So this is related to the fact that I said this function is always defined whether p is positive or negative if x is greater than 0. Not always defined if x is less than 0. Okay. Another example, cube root of x. Well, this is a non-integer. If p is 1/3, since the cube root of x is x to the 1/3. P is not an integer, but the cube root of x is defined for all values of x, isn't it? So, here's an example of a non-integer power that isn't defined when x is less than 0, but here's an example of one that is defined when x is less than 0. Now, we're not going to try to summarize every possible statement about the domain of these functions in this brief introduction. We'll say more later, but we get the idea that different power functions have different domains, and of course they have different ranges. And the domain and the range pretty much depend on the nature of p, whether it's positive or negative, whether it's an integer or not, and a number of other things. Whether it's an even integer, where it's a rational number with a even denominator, rational number with an odd denominator, but we don't really want to talk about that yet.